Differentiation rules. After having run through the limit definition of a derivative to both find the slope of a tangent line and find the derivative of a function, it is time to dig a little bit deeper and explore the patterns of derivatives. But before we get into these differentiation rules, I want to go over a bit of notation. Some of the notations for derivatives. Let's say you have a function f of x that is 1/2 x to the fourth minus 3x. One way you have already seen to know that your objective is to find a derivative is this direction to find f prime of x. And that's good. This is letting you know you're trying to find the derivative of a function. This is not the only notation that can be used. You could also see something that looks like this: d dx f of x. And this means we are going to take the derivative of f of x with respect to x. X is the variable that we're trying to find the derivative of. So this could be rewritten as d dx of 1/2 x to the fourth minus 3x. These two things are exactly the same because f of x equals 1/2 x to the fourth minus 3x. And since you all know that f of x is just a really fancy way to write y, we could also rewrite this as d dx of y, or more succinctly, dy dx. And over here, we could just write y prime. And these will be the most common ways that you see things written, like this d dx or dy dx or f prime of x or y prime. Now, if the variable changes, for example, if this function I had written as f of t equals 1/2 t to the fourth minus 3t, then we could find a derivative of that d dt of f of t. And so what will end up happening is, or what you'll end up noticing is, whatever variable is in the denominator here, that is the variable that is being used in the function. We will go over what happens when that is not the case a little bit later. But for right now, we will be taking the derivative, for this example, the derivative of f of t with respect to the variable t. Let's take a look at those rules. Differentiation rules. The first set of rules get summed up in a theorem. If f and g are differentiable functions, then so are f plus g, f minus g, and k times f, where k is some constant. This is good information, but without knowing what the derivatives look like, this is not very helpful. The derivatives are as follows. The first two rules oftentimes get grouped up into one rule called the sum and difference rule. And it says if you have the derivative, if you're finding the derivative of the sum of two functions, then you can find the derivative of each function individually and then add them together. Or this looks like f prime of x plus g prime of x. And by following the similar logic here, you can see that the derivative with respect to x of f of x minus g of x, the difference of two functions, will be the first function, the derivative of the first function minus the derivative of the second function. And the last one here is called the constant multiple rule. remember k is a constant. So if you have a constant being multiplied to a function, you can factor that constant out of the derivative and then take the derivative of the function at the very end. So the derivative of a constant times a function is the same thing as the constant times the derivative of the function. And these rules are meant more so for you to use than for you to be able to prove or to know. You won't have to go through and state, oh, well, I'm using the sum and difference rule here, or I'm using the constant multiple rule here. No, we will just go through and use these rules. On to the next set of rules. The second set of differentiation rules goes over some derivatives, some very common derivatives you will come across in your differentiation exercises. The first of which is the derivative of a constant is 0. We call this the constant rule. The second derivative is the derivative with respect to x of x is 1. The third derivative here, the derivative with respect to x of x to the n power is n times x to the n minus 1 power. And I want to put in here, there's a multiplication there. And we call this the power rule for differentiation. The fourth and fifth examples are the first trig derivatives that you will see out of the 6 trig functions. The first trig derivative is the derivative with respect to x of sine of x is cosine of x, and the derivative with respect to x of cosine of x is negative sine of x. And you can go through and prove these first two. In fact, you could probably go through and prove these first 3 if you wanted to. And you can use the limit definition as h approaches 0 all the way down with these first 3, and you should be able to come up with these answers, but I think seeing them geometrically also makes some sense. Down here in this graph, I have a constant function graphed here, y equals k. And if you take a look at any point on this graph, whatever point you like, it is a horizontal line. So you can pick any point, even the y-intercept, why not? Then you can see that if you want to put a tangent line at each of these points, you'll always get a line, a tangent line with a slope of 0. So when you have a constant function, the slope of a tangent line at any point there is 0. That's why the derivative of a constant is 0. Or maybe a different explanation as to why the derivative of a constant is 0. If you look at this next example, let's do this one in red. And you come over here and you plot the line y equals x, something like this. If you have the line y equals x, well, since it's again a linear function, any point you pick along this line, when you have a tangent line placed at all of these points, the slopes of all of those tangent lines will be 1. And so you can do something similar. It's not as easy to show in pictures why number 3 is true, but if you use the limit definition, you will get this exact answer here. It doesn't matter for what power. The power gets kicked to the front, and then you subtract 1 from that power. That's why we call it the power rule. And then with these last two, if you're really interested, you can send me an email and I will shoot you a link as to why these are true. And again, just like with the last set of rules, you don't need to know why these are true. You just need to know how to use these. So in the next few slides, there will be some examples. Very quickly on this slide, I want to talk about one more thing before we get into some examples, and that is the idea of higher order derivatives. And with the higher order derivatives, that means that if you have a function, yeah, you can find the derivative of it, but we call that the first derivative. But that creates a new function, which then you can find the derivative of, which creates a new function that you can find the derivative of, so on and so forth, forever, function willing. So normally we have a function that is f of x, or whatever variable is being used, and y, and we can use a couple different notations here. So let me create 3 columns here. So f of x, we have y, and we have another y over here. So in this first column, or in the first row, I should say, this is what all of the functions look like. And if you find the first derivative of f of x, that looks like this. And one way to write the derivative of y would be y prime. So that looks very similar to this one. But another way to write the derivative of y, which was already mentioned, would be taking the derivative of y with respect to x dx. So if we can keep finding the derivative of a function. So we can find the derivative and find the derivative of the derivative. So some notation would be like this: f double prime of x, y double prime, and then over here with the dy dx, this would be d squared y over dx squared. And that notation looks a little weird, but if you think of it like the first derivative being this, really the derivative is an operation, not just variables that we're throwing around. This can be rewritten as d dx of y. So we're taking the second derivative of y with respect to x. So that's why these 2's are placed like this. The third derivative would look something like this: 1, 2, 3 primes x. You could have y 1, 2, 3 primes, so f triple prime, y triple prime. And then over here with this notation, d cubed y over dx cubed. And again, you can follow the same notation for that. Any other derivative that goes higher than 3, we start using numbers in these 2 notations here. So just to give you an idea of what the fourth derivative or anything after that looks like, fourth derivative, this would be f in parentheses 4 x and y in parentheses 4. We put the parentheses around this just to make sure you understand that it is not an exponent. So this is mathematical notation. Parentheses around the number here and here means find the fourth derivative. And this number could change: 5, 6, 7, 8, 9, 10. All of these numbers would change, and then you would just have to keep finding derivative after derivative after derivative. This first example makes use of the power rule. You can see we have f of x equals x to the 8th power. So in order to find the derivative of this, f prime of x, I want to bring down the exponent to the front. So we have an exponent 8. So the 8 will come into the front as the coefficient now. And we still have an x, and then we take away 1 from the 8 power. Or more simply, 8x to the 7th power. There is the derivative of this function in under a minute. 8x to the 7th power. So in the second example, you can see we have g of x equals 7x to the 5th power. Because we have this constant 7 being multiplied to x to some power, we will use what we call the constant multiple rule as well as the power rule. So I say we will use these rules, but we're not going to actually go through and factor out a 7 like we did when I was explaining the constant multiple rule. Here's how this is going to work. You're going to pretend like this 7 isn't there. It's just going to come along for the ride. So over here, when we're finding g prime of x, I'm going to have 7 times. I'm going to use the power rule because I see I have x to a number power. So x to the 5th power. What did we do up here with this one? Well, we brought the power out to the front, the 8, and then we subtracted 1 from the exponent. So I'm going to shorten that up a little bit. So the power will come to the front, 5, x to the 4th power, right? Y'all know 5 minus 1 is 4, so I'm not going to do this notation anymore. So then the only thing we have to do is multiply this 7 times the 5 to give us 35x to the 4th power. Now in this last example, you can see that we have many terms. So 3x to the 4th minus new term, 6x cubed minus new term, 5x plus, there's another term, pi e squared. Okay, so I guess if we're going to do this, if we're going to find h prime of x, then we should use the power rule here, and I'm going to shorten this using the constant multiple rule, power rule. I'm going to shorten this even more. So up here, we could have just said, bring the 5 to the front. 7 times 5 is 35. I wrote it out so you could see what was happening, how the 35 showed up in the answer. But here, we can do this all in one step. We can bring the 4 down to the front. 3 times 4 is 12. X, take away 1 from this power, you're left with 3. Minus. All right, we can do the same thing here. We can bring this 3 to the front. 6 times 3 is 18. X, subtract 1 from the power. 3 minus 1 is 2. Minus 5x. Remember, the derivative of x is just 1. So 5 times 1 is 5. And this part was thrown in here just to shake you guys off a little bit. This is a constant. And when you take the derivative of a constant, you get 0. Now, mind you, we don't really write plus 0 here. So that's it. This is the derivative of h of x. Since we talked about higher order derivatives on the last slide, I would really like to show you how to find h double prime of x. And you can do that by taking the derivative of this function right here. So finding the second derivative would be starting with your function, finding the first derivative, and then taking the derivative of this to get the second derivative. So what I'm going to do is multiply this 3 out front to the 12 and get 36, and subtract 1 from this exponent to get x squared. In this term here, I'm going to take the 2 and multiply it to the front and get the negative 36, and subtract 1 from the exponent is just x to the first, and the derivative of a constant is 0, as we mentioned over here. We don't write that plus 0, but there that is. So this would be the second derivative of h of x. And one more for good measure. Let's find the third derivative here, h triple prime of x. This will be the last one we do for this example. Again, you can take that exponent, multiply it to the coefficient out front. 2 times 36 is 72. Subtract 1 from the exponent. In this case, x to the first power, 36 times 1 is 36, and then the x just kind of disappears. That's because when you have 1 power minus 1, it ends up being 0. X to the 0 power is 1. Again, we don't write it there, but that's what's happening. So here is the third derivative of h of x, or h triple prime of x. So check that out. We have done 1, 2, 3, 4, 5 derivatives in under 7 minutes. You're welcome. On this slide, 2 more examples. And I'm going to use this top one here to make this bottom one a little more understandable. You can see that in the denominator, for example 1 here, there is only one term. So that allows us to split this fraction into 2 fractions. Oops. So you have sine of x over 14 minus cosine of x over 7. And that's because when you split the 14 over here to the sine, there's nothing in front of it to reduce. But when you split the 14 over here into the 2 cosine x, 2 over 14 reduces to 1 over 7. So that's great. We turned one fraction into 2, and in most cases that scares students. However, this is actually much more helpful for us. But we still have a little more of rewriting to do with these before we can actually find a derivative. So I want to rewrite this just a little bit differently as 1 over 14 sine of x minus 1 over 7 cosine of x. And this gives us the viewpoint now that these numbers, 1 over 14 and 1 over 7, are in fact constants. So now we can go ahead and find the derivative of this function, noting that these are constants. So we just have to find the derivative of sine x and the derivative of cosine x. Well, easily enough, if you can remember back a few slides ago, the derivative of the sine of x is cosine of x, and the derivative of cosine of x is negative sine x. So I'm going to write sine x here, and the negative sine x will change this sign to positive. So f prime of x equals 1 over 14 cosine x plus 1 over 7 sine x. In this bottom example, we are going to do something very similar and knock out a few extra ideas in the process. So in the last lesson, I had a statement in one of the examples that said, recall x to the 1/2 equals the square root of x. So in order for us to use the power rule here, especially with the square root of x, we need to be able to represent it as an exponent, as a power. So square root of x is the same thing as x to the 1/2 power. So that's the first thing I'm going to do in my rewrite here. So this will equal x to the 1/2 power minus x to the 4th minus 3. all over x squared. Now the next step I'm going to do is something similar to what I did up here, split one fraction into many. All right, so that will mean g of x equals x to the 1/2 over x squared minus x to the 4th over x squared minus 3 over x squared. All right, so now what I want to do is simplify each fraction, and that's exactly what we did over here. Right, the 2 cosine x over 14 turned into cosine over 7 because the 2 over 14 simplified to 1 over 7. So now I'm going to simplify each of these fractions, and I'm going to get 1 over x to the 3/2 minus x squared minus 3 over x squared. So this last fraction didn't even simplify anymore, but we had more x's in the bottom than in the top here, so that means we had some left over in the bottom. In fact, 1.5 x's. X to the 4th over x squared leaves an x squared, and I already mentioned this does not simplify anymore. Now, in order to use the power rule here, we must have x's in the numerator. So we could find the derivative of this middle term right now, but this last term and this first term, we cannot find the derivatives of these until we get x in the numerator. So what we will do is we will rewrite this function with x in the numerator. So if you want to push an x from the denominator up into the numerator, you will simply make the exponent negative. So here we go. This is minus x squared minus 3x to the negative 2 power. All right. Now we can use power rule. So that means we bring down this exponent here. So this g prime of x, because this is where the actual derivative, where the actual calculus happens. All this other stuff over here was algebra. All these previous steps were algebra to make calculus possible. So the calculus step here is to bring down the exponent and then subtract 1 from the exponent, minus bring down the exponent and subtract 1 from the exponent, which leaves us with a 1, even though we don't write it. Then we bring down this exponent, so negative 2 times negative 3 is in fact a positive 6x, and when you subtract 1 from the exponent there, you get a negative 3. So this, which you're about to hear, is one of the simplifying or prettifying, making it pretty techniques. You don't want any negative exponents in your answer. So just as easily, like from this step to this step, as we pushed our x's to the numerator so we could take the derivative, at the very end we need to push them back down to the bottom so that we can make our answer look mathematically pretty. So this means negative 3 over 2x to the 5/2 power minus 2x plus 6 over x cubed. And this is now the derivative of g of x. Now those steps I mentioned, that those extra little things we threw in along the way, here's one. You need to make sure that if you have a square root of x, you need to represent it as x to the 1/2 power. Your mathematical life will be so much easier because of that. Again, just like in this example, splitting apart into 3 fractions because we had 1, 2, 3 terms in the numerator. And we were allowed to do that because we had one term in the denominator. The next thing that I threw in along the way was rewriting x's in the denominator as x's in a numerator by making the exponents negative. And that is what allowed us to do the calculus. At the very end, make sure if you have any negative exponents, you push them back down to the bottom of the fraction. In this example, you can see that we have this function here, f of x equals 5 times the cube root of x plus x, and you're being asked to find the equation of the tangent line passing through this point. So I think the first thing that I want to do is figure out what f of 1 is. And so if you can figure out f of 1, that means you replace all of these x's over here with 1. And that means that f of 1 equals 6. So that's a good bit of information to know. The next bit of information we need to know is what f prime of x is. But before we can do that, we need to rewrite x, the cube root of x as x to the 1/3 power, so we can use the power rule for this term. So the derivative f prime of x will be 5 times 1/3 x raised to the negative 2/3 power plus 1. That is, the power comes to the front. You subtract 1 away from 1/3, you get negative 2/3. The derivative of x is 1. Now if we just multiply these two numbers together, this 1/3 and this 5, you'll see that we get 5/3 x to the negative 2/3 power plus 1. And just to make it understandable, I want to write this as 5 over 3x to the 2/3 power plus 1. And that's what will give us the slope of the tangent line, which is part of what we need. We're looking for the entire equation of the tangent line. This will just give us the slope. So if we figure out what f prime of 1 is, that will actually give us 8/3. So this is the slope of the tangent line here. You can double check that for yourself. If you substitute 1 in here, you'll get 5/3 plus 1 is 8/3. Then we can just use the equation of a line. And you know that the slope of the tangent line is 8/3. We just computed that. And then way back over here, x is 1 and the y value is 6. So here we have 6. Here we have 1 plus b. And when you solve this for b, you end up with b equals 10/3. So with that, then the final equation will be y equals 8/3 x plus 10/3. Thus, this is the equation of the tangent line at this point on this function. On this slide, we return back to physics. This is something that you've seen before in a previous lesson. With the physics, we have s of t being the position function, v of t being the velocity function, a of t being, I don't have it written over here anymore, the acceleration function. But we talked about the velocity function being the derivative of the position function and the acceleration function being the derivative of the velocity function. But now with this idea of higher order derivatives, we can also say that the acceleration function is the second derivative of the position function. So if you have the position function and you take the derivative, you get the velocity function. If you take the derivative again, you get the acceleration function. This here, average velocity, we've mentioned before, or I've mentioned before in a previous lesson, in that if you're looking for speed, speed is the absolute value of the velocity.